Hello dear students, welcome you all. In this lecture, I'm going to take up the next topic of nuclear physics. The chapter that we are discussing here is nuclear models, right? So in the previous lectures, I have discussed about the liquid drop model of atomic nucleus. We have discussed about the semi-empirical mass formula. We have seen that the liquid drop model of the atomic nucleus was successful in explaining many features of the atomic nucleus, particularly nuclear fission. But it has several drawbacks. And the existence of the magic numbers nuclei in the nature is one of the major drawback of the liquid drop model, because it was not able to explain the existence of magic numbers in the nature, right? So first of all, in this lecture I will discuss about the magic numbers and their experimental evidences in the nature, and then in the consequent lectures I will discuss about the shell model of the atomic nucleus, right? So I'm coming to the magic numbers, right? So it has been observed that in nature, those nuclei for which either Z or N or both, they are equal to any of these numbers: 2, 8, 20, 28, 82, or 126, right? So on. These nuclei are highly stable as compared to their neighbors, right? What I said? I said that those nuclei which has either number of protons Z or number of neutrons N or both, right? They are equal to any of these numbers: 2, 8, 20, 28, 50, 82, or 126. Those nuclei are extra stable as compared to their neighbors, right? So this feature was not explained on the basis of liquid drop model of the atomic nucleus. Why this strange thing is happening in the nature? Why these nuclei are more stable, right? So these numbers 2, 8, 20, 28, these numbers are known as magic numbers in the nuclear physics. And the nuclei which have either number of neutron, number of proton, or both equal to these numbers, those nuclei are known as magic nuclei, right? Now I'm coming to the experimental evidences, right? What are the experimental evidences that pointed out toward the magic number and magic nuclei? So if I talk about the winding energy curve, let me draw the winding energy curve roughly here. This is the one axis, and this one. Now, we have discussed the winding energy curve in details in the unit number 1, right? And we have seen that in winding energy per nucleon curve, let me draw it here. This is binding energy per nucleon mass number, and this is mass number this side. So we obtain the winding energy graph of this type, like this, right? This is the rough draw of this winding energy per nucleon graph or curve. So we have seen at that time that in this graph we obtain sudden kinks in the graph. I mean, there is a sudden increase in the winding energy per nucleon in this graph at certain points in the graph. So these kinks, these sudden rise in the winding energy corresponds to obviously more stability, right? So at that time we were not able to explain it, why this feature is happening in the atomic nuclei, why certain nuclei have a very high winding energy as compared to their neighbors, right? These kinks, these sudden peaks in this winding energy graph, it point out toward the existence of extra stable nuclei in the nature. So this is the first experimental evidence. When we studied experimentally the stability of and binding energy of all the nuclei, then we found this feature. So this is the first experimental evidence that we got. And if we write down about those nuclei which have high winding energy as compared to their neighbors, they include 2He4 helium, right? 4 beryllium 8, we have seen it. Then 8 oxygen 16, right? Then 10 neon 20, right? All these have high winding energy. Then we have 38 strontium 88, right? Then 50 tin, right? 120. So all these are, this list is quite long. These are the nuclei at which we got a sudden increase in the winding energy, right? Or peaks in the winding energy curve. So this is the first experimental evidence that point out toward the existence of magic numbers. Sorry. Now I'm coming to the second one. We know very well that the stability of any nuclei is related to the abundance of that nucleus in the nature. So if we look at the natural abundance, I mean those nuclei which are found in abundance in the nature, then we observe that the nuclei like 8 oxygen 16, 20 calcium 40, right? Then 50 tin 120, right? Or 38 strontium 88, these nuclei, or 82 lead 208, these nuclei are abundance in the nature, right? Like helium 2He4, it is also abundance in the nature. So these nuclei are abundant. They are commonly found in the universe. It means these nuclei definitely have extra stability. That's why they are abundance. If they are not extra stable, then they would have been decayed into some other nuclei, and their abundance won't be there, right? So if their abundance in the nature, right, they are found in excess in the nature, it means they are extra stable, right? So this is the abundance. Natural abundance is the second experimental evidence, right? Now I'm coming to the third one. Third one is related to the stable isotopes. We know very well that what is a isotope. Isotope is that nucleus of a particular element which have same atomic number but different mass number. I mean either it has different number of neutrons, right, in the nucleus, right? Like 1H1, 1H2, 1H3, right? So if we look at the stable isotopes data in the universe, then we found that for calcium, if we take the case of calcium 20, calcium 40. So if we look at the data of calcium, then it is found that it has 6 stable isotopes, right? But if we look at the average number of stable isotopes in the region 1 to 20 atomic number, right, in the region of Z is equal to 1 to 20, then the number of stable isotopes in this region is about 2 for average number of stable isotopes for all the nuclei that exist in this range, right? Sorry. So if calcium has more number of stable isotopes, right, then it means this nuclei is having extra stability. That's why it is existing in multiple isotopes forms in the nature, right? Similarly, if we go to the tin, Z is equal to 50. We know very well for tin Z is equal to 50. We represent it as 50 SN 120. Sorry. So if we look at this, then it is found that it has 10 isotopes, right? 10 stable isotopes, right? Now, if we go to the region from 20 to 50 atomic number, we look at all the elements and all the nuclei that exist in this range, then the average number of stable isotopes is about 4, but this has 10. So again, this thing is pointing toward extra stability feature of this nuclei, right? So existence of more number of stable isotopes of a particular nucleus point out that that nucleus is extra stable, because the nucleus will prefer to have either Z or N as a magic, and in that sense that will exist in multiple forms. It will try to go toward either Z or N as a magic, right? So for doing that, that nucleus can exist in multiple forms. Similarly, if we look at the other, magic nuclei, then even then in those cases we found more number of stable isotopes, right? Now I'm coming to the point number 4, or evidence number 4, right? Now evidence number of 4 is when alpha particle is emitted from a nucleus, right? We know very well that alpha particle is basically helium, nucleus to He4. So if a nucleus, suppose this is a parent nucleus, it convert into a daughter nucleus, right? Daughter nucleus plus helium nucleus, that is alpha particle to He4, right? Now if the daughter nucleus that is formed is a magic nucleus, right? When there is a alpha decay and the daughter nucleus that is formed is daughter nucleus. So in that case, the energy of the alpha particle that is emitted is very high, right? It means this nucleus that we got after this conversion definitely have extra stability. That's why we are getting extra energy emitted in this process that is taken by the alpha particle, right? So it is again pointing out toward the extra stability of this daughter nucleus, right? So emission of alpha particle of larger energy when the daughter nuclei are magic nuclei is also a indication toward the existence of magic number. And in converse, if the daughter nucleus is not stable, if the parent nucleus is magic, right? So in that case, if there is a alpha decay, then we will get only very small energy of the alpha decay and very small probability is there for the alpha decay. So alpha decay and the energy of the alpha particle emitted, right, is an indication toward the existence of magic numbers, right? Now I'm coming to the next evidence number 5, right? Now if we look at the 4 radioactive series, we'll come to these radioactive series in the radioactivity chapter, radioactive series. At this point, I want to tell you that there exist 4 radioactive series in the nature. We will discuss in the details in the radioactivity chapter. And in all those 4 radioactive series, the stable end product is lead, that is 82 lead. Now it has different isotopes 206, 207, 208. But it is the stable end product in 3 radioactive series out of 4. Total 4 radioactive series exist in the nature. Radioactive series contains all the radioactive elements that we observe in the nature. So we have total 4 radioactive series. It means in 4 series, all the radioactive nuclei are included, and the stable end product of all the those radioactive elements or radioactive nuclei is in 3 out of 4 we have lead. So we know very well 82 lead. It is an indication of extra stability of this 82. And if we have 208, then even in that case, we got both N and Z as a magic, right? So radioactive series, the experimental evidence that comes from the stable end product of the 3 radioactive series also point out toward the extra stability of these magic nuclei, right? Now I am coming to the next point, next evidence. It is quadrupole moment, right? It has been experimentally observed that if the nucleus is magic, right, in that case the quadrupole moment is equal to 0, right? And if the nucleus is non-magic, then it is not equal to 0. So if the nucleus is magic and the quadrupole moment is 0, it means all the charge inside the nucleus is uniformly distributed, and the nucleus has a spherical symmetry, and it is having extra stability. So the existence of 0 quadrupole moment for the magic nuclei is also an indication of the extra stability, because the quadrupole moment will be zero only when the nucleus is spherically symmetric. There is no distortion in the shape. There are no oscillations in the nucleus, right? And it is totally stable. So in that case, the quadrupole moment will be equal to zero. But if the quadrupole moment is not equal to zero, it means the nucleus is definitely have some distortions. Its shape is not perfectly sphere, and in that case, there is a probability of alpha decay or a beta decay, and we can say the nucleus is non-stable. But if the quadrupole moment is zero, the nucleus is highly stable, and it is obviously having magic number of either neutron or a proton. So it has been experimentally observed that those nuclei which are magic, they have quadrupole moment equal to zero, right? Now I'm coming to the next point number 7, evidence number 7, right? So point number 7 is when we look at the doubly magic nuclei. Doubly magic nuclei means those nuclei in which both number of neutron and number of proton are magic. For example, 2He, 4, 8, oxygen, 16, 20, calcium, 40, 82, lead. I'm taking some example, 208. If we look at 2, both Z and N is equal to 2, both Z and N is equal to 8, Z and N is equal to 20, Z is equal to 82, 82, and N is equal to 126. So it is found that those nuclei which are doubly magic means both number of proton and number of neutron are equal to magic. They having very high winding energy, and their winding energy is even more than the prediction made by the binding energy formula. Even their energies, I mean, more than that calculations. So it means these doubly magic nuclei are very high stable, right? They having very high stability. So it is again pointing toward the existence of these magic numbers, right? Extra stability associated with these numbers, right? The next evidence comes from the beta decay process. So again, it is found just like alpha decay, when there is a beta decay and the daughter nucleus is magic. It is magic, then the energy of the beta particles emitted, whether they are electron or a positron, it is very high as compared to the case when the parent nucleus is magic, right? If the parent is magic, then the energy is low. But if the daughter is magic, energy is high. So it is again an indication that after the beta decay, the nucleus that is formed, that is definitely having extra stability. That's why the energy released is more, right? Because more energy released means higher stability. But if the energy released is low, then it means the nucleus that we got after this, that is definitely have a low stability. So these are some points. I'm taking the last one, that is cross section, neutron capture cross section. Capture cross section. It is found that neutron capture cross section means if we are hitting a nucleus with the neutron, then if the nucleus capture that neutron, then we count that probability in terms of a nuclear capture cross section. So it is found that if the nucleus that we are hitting with the neutron, if it is magic, right, then in that case neutron capture cross section will be very low. What I said you if I have a nucleus, right, and it is a magic nuclei, and I am hitting this nucleus with the slow moving neutron. So in that case, if this nucleus is magic, there is very low probability that this neutron will be captured or absorbed by this nucleus. But if it is non-magic, then there is definitely high probability that neutron will be captured by the nucleus, and then after this nucleus can further disintegrate, right? either into two or more than two products, or even it can do alpha decay or some other kind of nuclear reaction, right? So these are the 9 experimental evidences that points toward the existence of these magic numbers in the natures and these magic nuclei in the nature, right? So this existence of the magic numbers and magic nuclei lay down the foundation of a shell model of atomic nucleus, because this feature is not explained by the liquid drop model, as I told you. So in the coming lecture, I will discuss about the nuclear shell model, right? So thank you very much.